All right, so welcome back. I think this is video 3 for this section. So we're going to take a look at some slightly more complicated examples performing these solutions or finding these solutions using the echelon method. And so I have two of them on here. We'll start with the one on the left, so make this a little bit bigger so it can take up as much space as possible. Our directions are for each of the following systems, determine how many solutions there are in the non-negative integers. Okay, so let's take a look at some stuff before we get into the meat of it and talk about what's going on here. First, I hope that you notice that while there are 3 variables in this system, there are only 2 equations. And since there are fewer equations than there are variables, this guarantees that we're going to have to parameterize this solution, which is why the directions are asking about finding all of the solutions that are in integer values, non-negative integers, because infinitely many, but of those infinitely many solutions that exist, only some of them will be non-negative integers, like 1, 2, 3, 4, and so on all 3 variables. All right, so let's get into the meat of this. To solve this, since it will be parameterized, I need to find solutions for each of the variables x and y in terms of z. Now remember, when we parameterize, we almost always parameterize on the rightmost variable, in this case z. And the reason we do that is it's just convention, but if we knew z, we could find y in the second equation. Like if I knew z was 5, we could solve for y in the second equation. And then we could take those 2 values for y and z and put them back into the first equation and find an x. So let's go ahead and start doing that. I am going to start by taking this second equation and solving for y in terms of z. The system is already in echelon mode, if you will, because there's no x in the second equation, and there's no third equation to take the y out of, so we're already there. So we'll just start parameterizing. If I take a look at that second equation, I could say that 3y is equal to 36 minus 4z by just simply subtracting the 4z to the right-hand side. I could then remove that coefficient, that 3, by dividing through by 3, and I would get that y is equal to 12 minus 4/3 z. And now I have y in terms of z. The next thing that we'll need to do to finish this parameterization is to find x in terms of z. So I'm going to take this and I'm going to put it back up in here to that first equation for y, do a back substitution. Then I'll have a single equation with only x's and z's in it, and we'll be able to solve for x in terms of z. So I'm going to go ahead and bring that down here. That's going to give me x plus 2 times 12 minus 4/3 z plus 3z is equal to 90. We've got some distribution to do here, so I'll do that distribution. I'm going to have x plus 24 minus 8/3 z plus 3z is equal to 90. Now I'll gather up some like terms. I got like terms here and here. And so I'm going to have x plus 24. Remember, 3 can be thought of as 9/3. So negative 8/3 plus 9/3 will give me a positive 1/3 z is equal to 90. Now I'll move both the 24 and the 1/3 z to the right-hand side, and that's going to give me that x is equal to negative 1/3 z. 90 less 24 will be what, 66? Plus 66. Now I'm at a point where I know both x and y from earlier in terms of z. So if you told me what z was, I could find a value for x and I could find a value for y. Now if I go back up here and take a look at the directions, remember, they want us to determine how many solutions there are in the non-negative integers. So I want to just talk about our solution right now. Our system has a parameterized solution of negative 1/3 z plus 66 for x, 12 minus 4/3 z for y, and then z is just allowed to be z. Now, mathematically, this represents infinitely many solutions. But realistically, some of those solutions for z are going to give us positive answers for x and y. Some of those solutions for z are going to give us negative answers for x and y. And so what we need to do is we need to figure out what we've got to do to make sure that our answers end up being positive integers. So probably the easiest way to do that is just to start with the smallest answer that z could be and go from there. Now I realize I just said positive integers, but they just want actually non-negative integers. And positive and non-negative aren't the same thing because of this guy, 0. 0 is not negative. It's also not positive, but if they want non-negative, then I got to think about 0 being a possible answer too. So I'm going to come down here and I'm going to make a table. And that table is going to give me all of the possible answers for x's and y's and z's. So my z is just going to be z. My y's are going to go here. My x's are going to go here. Remember, x is negative 1/3 z plus 66. Y is 12 minus 4/3 z. Now the smallest number that's not negative and an integer would be 0 for z. And if z was 0, then y would be 12 and x would be 66. Okay. Well, the next non-negative integer that z could be would be 1. But if I try to put a 1 in for z in my x's and y's, I'm going to get 12 minus this one right here and this one right here. They're not going to be integers, right? That second one is going to be 12 minus 4/3 z, so that's what, 32/3? That's not an integer, so that answer isn't going to work, right? In fact, there's a shortcut here. Did you notice that both the x and the y parameterization had a third in them? So to make that work, z is going to have to be a multiple of 3. Otherwise, I'm going to have fractions, and 66 minus a fraction or 12 minus a fraction is still going to be a fraction, not an integer. So actually, the next number that's going to work for z would be 3. And if I do some scratch work over here, to find the y would be 12 minus 4/3 times 3. Well, those are going to cancel, so 12 minus 4, that just gives me, what, 8? And then x is going to be 66 minus 1/3 times 3. 3 is going to cancel, so that would be 65. So I get 65 and 8. Continuing down that thought, if z has to be a multiple of 3, the next thing it could be is 6. So then over here, I'll do my scratch work, and I ran out of room, so I'm going to have to erase as I go kind of thing. So this would be 12 minus 4/3 times 6. So that's going to be 12 minus 8, or 4. This would be 66 minus 1/3 times 6. So that's going to be 66 minus 2, which would be 64. Right. Now, luckily, in most of these problems, there's going to be a pattern that's going to be hidden in the numbers. And you'll see here, every time z goes up by 3, y goes down by 4, x goes down by 1. So if z goes up by 3 again, y would go down by 4, and x would go down by 1. And if we tried to make z go up by 3 again to 12, well then this would go negative, and that's not going to be a solution because we're supposed to find non-negative solutions. Now actually, the answer to the question is not these 4 solutions we found, because the question asks how many solutions there are in the non-negative integers. And so there are 4 solutions. Now, if I needed to write them out, I could. One solution is 66, 12, 0. A second solution would be that 65, 8, 3. A third solution would be the 64, 4, 6. And our final solution would be that 63, 0, 9. All 4 of our solutions. And so this is what we're looking at for the answer to this problem. Now, they gave us 2 examples here, but the directions are the same for both of them. So it looks like this one over here is going to be the same problem again. So I'm just going to go ahead and work through it. I'm going to move a little faster on this one since I kind of know what to do. I'm going to parameterize on z again. So I'll solve that second equation for z. So 2y is equal to 60 minus 7z. That's going to give me y is equal to 30 minus 7 halves z. Right? I'm going to take that answer. I'm going to back substitute into the first equation to go solve for x in terms of z. And so that's going to give me x minus 7 times 30 minus 7 halves z plus 4z equals 75. Whoops, that parentheses shouldn't be there. That parentheses should be there because the negative 7 is only multiplied by the y value. The y value. So let's see, x minus 210, that's the 70 times 30, plus 49 halves, that's the negative 7 times the negative 7 halves z, plus 4z equals 75. Now I need to combine some like terms here. And so that's going to give me x minus 210. Let's see, 4z, I could think of that as 8 halves. So 49 halves plus 8 halves would be 57 halves. So plus 57 halves z is equal to 75. Now I'm going to take the z term and the constant term and move them to the right. Let's see, we'll go to red. And so that's going to be x is equal to negative 57 halves z. And then I'm going to add the 210, so plus 285. And so now I've got x in terms of z. Now I got to do that business where I'll make that table again to try to figure out how many of these are non-negative. So my table is going to have x's, y's, and z's. But when I want to find out y, I'm going to take 30 minus 7 halves z. And when I want to find x, I'm going to do that business. Now, I saw a pattern before, and I'm going to try to use that pattern to make my life better. My denominators in both of my parameterizations are 2. So that tells me that z is going to have to go up by 2 each time. Now I'm stopping at 6 because I don't know how far to go. If I have to add more, I will. The y's are going to go down by 7 each time, right there. And the x's are going to go down by 57 each time. So the y's will start at 30. The x's will start at 285. But when I go up by 2, y's go down by 7, which takes me to 23. And the x's go down by 57. So then I got to do 285 less 57. Yuck, that's ugly. How about we make that be 288 minus 60? That seems easier. So 228. So 228. And then we go up by 2, so this one, so the y's will go down by 7 again. 23 less 7, I think, is 16. Yeah. I got to go 228, and then I got to subtract from 228 another 57. I don't like that. So let's make that 231 minus 60. So that's 201 minus 3, so 171. Sounds good. 171. Z goes up by 2. Y goes down by 7, so we're to 9. And now I got to do 171 minus 58. No, 57, sorry. Let's do 174 minus 60. So you notice that I'm just adding 3 to both numbers each time? Because if you change them both by the same amount, the answer is still the same. So that's 114. And then it looks like we need more z's. So it looks like we could go up to 8. This would go to 9 minus 7. That would go to 2. 114, 114 minus 57 is 117 minus 60. Let's see, what is that going to be, 57? Now, can I go bigger? Well, no, because if I go bigger on z, then y is going to go negative. If I try to take this up to 10, then this is going to go negative because we're subtracting 7, so that won't be an answer. So it looks like this guy's got 5 solutions. So I'm counting 5 non-negative solutions. And if I needed to list them, they're all right there. I just write them as ordered triples. Okay? All right, well, I hope that worked. This is kind of a lot, but the math is pretty easy. Now you're going to see this concept again. You're going to see this concept of how many solutions there are of a certain type. It's almost always going to be this business, this non-negative integer. And the reason is where we're heading is word problems. And in word problems, the variables x, y, and z mean something. And a lot of times, the way we define our variables will be this can't be a piece and a part. It can't be a half or a third. And so it can't be fractions. It has to be integers. And then negative numbers wouldn't make sense because if you're counting something, you could never have -3 of it. All right. Hope that makes sense. I'll see you back here for the next video.